When building a neural network model for a new problem or a new data set, the biggest question that you may ask is, what is the best setting of my model? That is, what kind of model, neural network model, should I build to deliver the highest performance on my validation set? We know that model consists of a lot of weights and bias values. These are known as the parameters of the model. And because we have no control over them, we do have control over them, but we have indirect control over them. The optimization process automatically updates these weights. But what we have control over is either the size of the neural network, that is, how many layers we want, in each layer, how many neurons we want, how many epochs to train, what batch size to use, what activation functions to use, what loss functions to use, and so on. All of these parameters, which we have control over, that eventually change the parameters of the model, are known as hyperparameters. And it makes sense because these are parameters that actually control the parameters of the model. Now, to answer the question about what kind of model configuration or what kind of my neural network model gives the highest performance on the validation set, the answer is the best tuning of these hyperparameters. We have to keep playing around with the number of neurons in each layer, the number of layers in the network, the number of epochs, batch size, various activations, various loss functions, and all of these things to find out what combinations of these hyperparameters lead to the maximum accuracy or performance on the validation set. Unfortunately, there is no universal rule or universal principle to find these hyperparameters. And this is exactly why many people argue that machine learning is more like an art, where you have to keep playing with these parameters to find out what works best. Now, obviously, we can always tune these hyperparameters and maybe even make them as high as possible. For example, increase the number of epochs to 1,000, make a neural network that has 8 or 9 layers, and then also the number of neurons in each layer to be very high. But then we know that that's going to give a very high accuracy on the training set, but not on the validation set, probably. So the optimal setting of hyperparameters is the setting where we get a very high accuracy on the training set, but also a very high accuracy on the validation set. So if the number of parameters or the kinds of parameters we choose, the hyperparameters we choose to tune the model give a very high accuracy on the training set, but not on the validation set, then we end up overfitting the model. If we don't play around a lot with these hyperparameters and choose a very tiny model to train, then we may be underfitting. We may just be catching a few patterns in the data and not actually capturing all the rich patterns that the data may have. So this will lead to underfitting, and this will result in poor performance both in the training set and the validation set. So the key here is to play with all of these hyperparameters, keep testing various options that you have, and then find an optimal setting. In all of the machine learning and deep learning research I do, almost all of my time is spent on fine-tuning these hyperparameters. I'm always playing around with the optimal batch size, a batch size that allows me to use the GPU more optimally. I'm always testing how deep of a network I can build and how long I should train my model, and so on. If you enjoy this process of hyperparameter tuning, machine learning is a lot of fun. The real joy comes from playing around with these hyperparameters and finding an optimal set where you get the highest performance on the validation set. Now, it is very common to feel a little uncomfortable and not very satisfied with the parameters that you may have. This is okay. We play around with the parameters as much as we can, and given the time frame and given the resources we have, we choose the best parameters we can.